Welcome to homework.
One of the surprising ways that you can use the Bohr model of the atom is in semiconductor physics, where we can consider the binding of an electron to a positive charge in a crystal, but we are assuming that the space between the electron and that positive charge is filled with a dielectric material, in this case silicon, with a relative dielectric constant, we'll call it a big kappa, equal to about 10. And so we want to use the Bohr model to recalculate the energy levels in this case, with the understanding that the effective mass of an electron inside of a crystal is not the same as the mass of the electron. It is about 20% the mass of the electron. So the parts of the Bohr model are, first of all, use the electric force to provide centripetal force on the electron. So that's the effective mass, v squared over r. And here the force of the Coulomb force is going to be reduced by a factor equal to the dielectric constant. And that is because there will be polarization set up in that green substance. The polarization will create a field opposite the electric field between the two. Actually, the electric field created by the positive charge. So we are going to put the electric force as the Coulomb's law, but with the electric constant K reduced by a factor equal to kappa. It looks a little awkward, but yeah, we'll use kappa. There is another symbol we could use, which is the relative permittivity of free space. We could use that symbol as well. But we'll go ahead and use kappa. And then the product mv squared, if we reduce the factor in the denominator, we have a factor for mv squared. The second thing that we can use is the quantization of angular momentum. Will look the same, except we'll use the effective mass of the electron, but there's no dielectricity in that relationship. And the third thing that goes in is the energy is equal to the kinetic plus the electric potential. And again, that electric potential energy will be reduced due to the dielectric, reduced interaction between the electron and the positive charge in the crystal. And of course, the kinetic energy will use the effective mass of the electron. So yeah, and really the thing to think about, I can write this off to the side, K is equal to 1 over 4 pi epsilon, and epsilon is equal to kappa times epsilon 0. That would be a more proper way to write it, but I am using, in my case, I am using K equals 1 over 4 pi epsilon 0 and showing explicitly the kappa. Anyway, the energy will look like minus 1/2 Ke squared over kappa r. We can use the second equation to replace the velocity in terms of the radius and the effective mass. And then we can put this velocity back in to equation 1 and solve for the radius. So we'll eliminate V by using equation 2. And we will get R as a function of n, which we can then use in equation 3. But R sub n, okay, that's good to see how this works, is kappa n squared h bar squared over the effective mass times Ke squared, the electrical K. And then we can substitute this in to our energy relationship. And so we get E as a function of n, putting it all together, is minus 1/2 Ke squared squared over n squared h bar squared times the effective mass and then the dielectric constant shows up as squared. Okay, so we can kind of simplify this new energy relationship because the cluster of constants out in front is simply minus 13.6 EB over n squared. If we get the electron mass in there. So we're going to write the effective mass as ME divided by ME. You can always multiply in terms of 1. And so we finally have the E sub n is minus 13.6 electron volts over n squared times the ratio of the effective mass to that of the electron divided by the dielectric strength squared. So note that everything off to the side here is new and it is unitless. The stuff to the right of that, or the left of that, sorry, is the energy levels in regular hydrogen. So we see that the dielectric constant reduces the binding energy by a factor of kappa squared, and we get a further reduction by the effective mass inside the crystal being less than the mass of the electron. So finally, we can use the En to find the binding energy of the electron in arsenic-doped silicon. Okay, so we're basically going to take the absolute value of E1 would be the energy needed to remove the electron from the ground state of this system. And that would be 13.6 electron volts. The quantity in blue parentheses is 0.2 divided by 10 squared. And that comes out to be 0.027 electron volts.